All right. Okay, so let me give some other scenarios for you to say what the flux should be. Okay, so let's say scenario 3. What if I have Wi equal to 1 and the Wi plus 1 equal to 0, right? In this case, what should the flux be? Well, if you take the average of the solutions, it's half. If you take the flux of half, you get 1/8. That's definitely wrong, right? Now, if you take the flux, it's half on the left, 0 on the right. Now you take the average, it's going to be a quarter. It's different from 1/8, but still wrong. Like, what should be the flux over here? 1/2? Why? 1/2 is correct. Why? The discontinuity actually is not going to be still there. In this case, the discontinuity, well, it's still there, but it's not going to be there at the same location. Yes, the discontinuity is moving towards the right because delta F over delta W is actually equal to what? It's equal to half, right? Okay, so the speed of the shock is going to move it towards the right. And how does that relate to the value of the flux?
Well, then you would just take the flux in the interior of the right-hand side.
So yes, again, the argument is after infinitesimal amount of time, what is the flux going to be? So after an infinitesimal amount of time, the shock would be moving to here, right? And then you take the value of the flux over here, which is half of 1, right? The Fi plus 1, half is equal to half in this case. All right? Okay, so let me give you another case. The fourth case is, okay, you have the solution being Wi equal to 0, Wi plus 1 equal to minus 1. What should the flux be after, or what should the flux be? Huh? 1/2, why? The shock would be moving towards the left, right? So it's still going to be 1/2 because after a little bit of time, the shock, I mean, in this case, delta W is still the same, but delta F is going to be minus half, right? So, yes. Okay, so let me give you another case that's a little bit the final case. So let's say Wi plus 1 is equal to 2, and Wi is equal to minus 1. All right. So what should the flux be in this case? Zero. Why? The discontinuity vanishes, and basically if you draw the x and t diagram, you have plus 2 on the left hand side, you have minus 1 on this side, and you have a solution that fans out. Always the solution where the characteristic is equal to 0 stays at 0, right? Right, so F would be equal to 0 in this case. Okay, so this is what the Goodenough scheme is about, right? The Goodenough scheme is trying to figure out, in all scenarios, what should the flux be after infinitesimal amount of time, and use that to construct the correct numerical flux. All right. So for the Burger's equation, we have pretty much figured out what to do, right? So first of all, we have to decide if the shock is going to disappear. I mean, if the discontinuity is going to disappear or stay as a discontinuity. That's the first question we want to ask. All right. And the second question we want to ask is, if it stays the same, I mean, it branches, right? So, okay, if it stays as a shock, which direction is the shock going to move? If it's moving towards the right, we'll take the flux on the left side. If the shock is moving towards the left, we take the flux on the right side. So for that, there is no difference between the Goodenough scheme and the upwinding flux scheme. But when the discontinuity is disappearing, then it's different. Okay? Then there are actually 3 different scenarios when the discontinuity is disappearing, which for Burger's equation is actually when the left is lower than the right. I mean, for other equations, it's different. For other equations, you have to do analysis, we'll say later, of is the discontinuity going to disappear or not disappear. So if the discontinuity is going to disappear, there are 3 scenarios. One scenario is the discontinuity is going to disappear and the whole thing is moving towards the right like this. Yes, it's going to disappearing, but because both sides are actually moving towards the right, so the discontinuity is going to be completely moved towards the next cell afterwards. The opposite case is that if you have a discontinuity like that, the whole thing is going to be moved towards the left. So in these cases, you take the flux on the left if whole thing is moving towards the right, or you take the flux on the right if whole thing is moving towards the left. Again, there is no difference between these 2 scenarios and the upwinding flux. Now we come to the final case where there is a significant difference between the Goodenough flux and the upwinding flux. That is when you have a discontinuity that will disappear. And one side is moving towards the left, the other side is moving towards the right. Okay, in that case, what should the flux be? Zero. Or, let me say it a little bit more general. Right? The flux should be the flux at which the df dw is equal to 0. Right? Does it make sense? Df dw equal to 0 means that what is equal to 0? What is df dw? The wave speed, right? So it is the wave speed, it is the value of w at which the wave speed is equal to 0, which means when I have a characteristic that fans out, that's the value that's going to stay stationary, right? The part of w on the higher than it is going to move to, I mean, for df dw higher than 0 is going to move towards the right. Df dw that is lower than 0 is going to move towards the left, and that point is going to stay. For Burger's equation, it happens to be 0. For other equation, that's not the case. Okay? Make sense?